Okay, so today I'm going to be talking about Hardy-Weinberg and how you can use this to estimate the phenotypes and genotypes in the population. This will be trying to simplify it and showing how it was derived and can be used. So first of all, we're going to look at an example of an intermediate dominance. So this means basically when two traits are mixed, neither are distinctive. So for example, the red plant and the white plant will mix together to make a pink plant. This is useful because you can see which flowers will have which genotype. So, for example, you can't have a C and a W, a CR and a CW always make pink, a CW and a CW always make white, and a CR and a CR will always make red. So just keep that in mind. So if anything has a CR, it'll have either be red or pink. If anything has a CW, it'll be white or pink. Here we go. So first of all, we'll have to look in a population of 100 plants. So we're going to kind of use this one example to talk through how to derive Hardy-Weinberg and how to use it. So let's look at red plants first of all. So there are 100, this was given. In the population, there are 64 red flowers. And they have the CRCR, the genotype CRCR. So we can have a look at how we're trying to find out how many CRs are in the whole population of 100 plants. So we can see that the 64 plants with CR. They both have one CR. They both have two CRs, so you multiply by 2. We can also see that a pink plant will also carry the CR genotype, so we have to add 32 to that, which gives us a total of 160. Now we're looking at a total of 100 plants, each having 2 genotypes, so give us 200 alleles, which give us 200. So we divide 160 by 200 to give us an 80% chance that the plant will carry a CR allele. So now we calculate how many white alleles are present. So we have obviously the CW white flower, which will and there's only 4 of those plants, so we calculate to be 8 alleles of the CW. We have 32 pink plants, and each of them carry 1 CW, so that gives us a total of 40. We multiply that by, we divide that by 200, as there's 200 total alleles in the population, which gives us a 20% chance of 0.2, and we were going to call that Q. So now we're going to start looking at the Hardy-Weinberg, just to simplify how this can be done. So the frequencies are designated P, Q, and R. All the frequencies of all the alleles must add to 1, 1 being 100%. So if you have 2 alleles, P and Q, they must equal 1. So in that example, we had 2 alleles, both P and Q, signifying a color, and they would equal to 1. So if P equals 0.8, then Q obviously must equal 0.2 because they have to add up to 1. So now we're going to look at this example. This looks a bit more complicated, but it's fine to show. So here we have up here, we have the CR with a P of 80 and a CW of a Q of 0.2. Now this was our original F1 generation, and they will be able to make CR and CW alleles, and also here the female will also be CR, CW. So these are all the possible alleles that can be made. Now, when we make these together, we get, it's the same as multiplying. So 0.8 multiplied by 0.8 is 0.64. CW, which is 0.2 multiplied by 0.8 is 0.16. Same here. And when you multiply 0.2 by 0.2, you get 0.04. And this is the same as writing P squared. So that's the same as writing P squared, is the same as writing P squared. So it'd be 0.8 squared. This is the same as writing P multiplied by 2. And this is the same as writing Q squared. And that's where we get our numbers from. Now, if you look at these numbers, they all add up to 1. 0.64 plus 0.18 0.16 plus 0.16 plus 0.04 will all add up to 1, which is what we were originally looking for. Now, this will only occur if this Punnett square has specific requirements. So the Hardy-Weinberg experiment, Hardy-Weinberg theory will only work with these specific requirements. So there's no mutations, there's no migrations, there's no migration in and out of population, random mating, so it doesn't matter what colors plants are, they're always mate randomly. There's no natural selection, so the plant's color does not affect their chance of survival, and there's obviously a large population, which we had, which was 100. Obviously in the wild it's to be much larger. So this is basically how Hardy-Weinberg is generated. So we saw that we could calculate homozygous CR/CR with red, which would be p squared. We saw that the homozygous CW/CW allele gave us q squared, and we saw that heterozygous CW/CR gave us pink, which was 2pq. And this right here with the red dot on it is the exact Hardy-Weinberg equation. And now we've seen how it came about. Thank you very much for listening.